The perfect storm, a Category 5 hurricane. Sustained winds exceeding 252 kilometers per hour. At this velocity, the atmosphere stops behaving like gas and starts acting like a solid wall of kinetic energy. For a standard skyscraper, this is an extreme structural test. But what if that skyscraper is covered in tens of thousands of living trees? Welcome to the ultimate engineering paradox, the hurricane-proof vertical forest. To a fluid dynamics engineer, a tree isn't just landscaping. It is a massive, unpredictable aerodynamic sail. Today, we break down the terrifying physics, engineering trade-offs, and brutal calculations required to keep this green megastructure from tearing itself apart. The physics of the living sail. When high-velocity wind hits a tree, it triggers aerodynamic drag. The fundamental equation governing this force is a foundational building block for wind engineering. The drag force equals 1/2 times the air density, times the wind velocity squared, times the drag coefficient, times the frontal area of the canopy. Notice that velocity is squared. If you double the wind speed from a normal storm to a Category 5 hurricane, the destructive force doesn't double, it quadruples. Based on high-confidence engineering estimates, a single mature tree with a drag coefficient between 0.3 and 0.6 can experience an overturning moment at its base exceeding 100 kilonewton-meters, 73,756 pound-feet, in Category 5 winds. Multiply that by 2,000 trees, and the tower faces millions of newtons of erratic dynamic lateral forces. If a single root system fails, that tree becomes a flying missile, shattering high-strength laminated glazing downstream. To prevent this, arborists and civil engineers must utilize species-specific crown thinning to lower the drag coefficient and anchor the root balls using subsurface high-tensile steel geotextile straps directly into the building's structural core. The structural weight and the liquid dead load. The second existential crisis is weight. A vertical forest requires thousands of metric tons of engineered soil, drainage layers, and water retention systems. When a hurricane hits, it drops torrential rain, often exceeding 150 millimeters 6 inches per hour. Engineers must design for the saturated dead load. Saturated engineered soil can weigh up to 1,500 kilograms per cubic meter, 93 pounds per cubic foot. This introduces massive eccentric loads on the cantilevered balconies, threatening to induce intense torsional or twisting forces on the entire skyscraper. To survive, the structural system relies on ultra-high-performance concrete, with a compressive strength exceeding 150 megapascals, 22,000 psi. This is paired with an advanced core wall system and deep outriggers to transfer these immense twisting forces safely down to the bedrock foundation. Vortex shedding and the monster in the wind. But the most terrifying threat isn't the direct push of the wind. It's what happens after the wind passes the building. This is vortex shedding. As alternating low-pressure eddies form behind the tower, they introduce a cyclic, rhythmic pull perpendicular to the wind direction. If the frequency of these vortices matches the natural resonant frequency of the building, the tower will undergo catastrophic aeroelastic instability. It will shake itself to pieces. Here, the vertical forest offers an unexpected engineering advantage: aerodynamic porosity. Unlike smooth glass towers that create perfect, destructive vortices, the irregular, porous canopy of thousands of trees breaks up the wind. The forest acts as a natural acoustic and aerodynamic damper, disrupting the formation of organized vortices. The final defense and verdict: to counter any remaining building acceleration and preserve human comfort limits, a massive 800-ton tuned mass damper sits suspended in the crown of the tower. As the hurricane pushes the building west, the computer-controlled active damper shifts east, stabilizing the structure in real time. Can engineering truly build a living, vertical forest to survive a Category 5 hurricane? The structural load path is verified. The facade resilience is achievable through rigid Miami-Dade impact-rated missile testing. Tree aerodynamics remain a challenge, but they show moderate confidence pending deeper boundary layer wind tunnel testing. It is a high-cost, high-maintenance battle of physics against nature, a testament to human ingenuity where architecture doesn't fight the elements, it adapts to them.